So, welcome student to the next class of Introduction to Nonlinear Optics and its application course. So, today the lecture number is 32. So, we will going to learn few important topics today. So, first topic that we are going to learn is three-wave interaction. In the last class we have already started the concept what is three-wave interaction and what are the nomenclatures for that. Then we try to find out the equation of pump signal and idler wave, and finally the non-collinear phase matching. So far we are dealing with the phase matching, and when the vector diagram of the phase matching was shown, it was normally collinear in nature. But now today we will going to show that if we generate some pump and signal and idler and pump, then it is not necessarily that they are same. So, that is why the wave vector may have a different direction. So, the phase matching may not be collinear in nature. So, there is a non-collinear kind of phase matching. So, in that case how to find out the phase matching and other issues we will going to take care. But before we will going to the non-collinear phase match, we will learn about the three-wave interaction. So, let us go back to the slides. So, three-wave interaction, as I mentioned, this is associated with three-wave as the name suggests. The nomenclature is I will going to launch one signal, and this signal, along with this signal, if I launch another wave, if I call idler, then this signal and idler they will going to form another wave, we called it pump. So, pump is nothing but the summation of signal and idler. So, this is, if I look carefully, this is nothing but the sum frequency generation. That means, in the previous cases we use omega 1 plus omega 2, which was omega 3. This is some sort of sum frequency. So, here we are doing the same thing, but we changed the name. Instead of using 1, 2 and 3, now we change the name as pump, signal and idler. That is first case or the first consideration. Second thing that one should remember here, that in this treatment always the signal will be here. So, every time what we will going to launch is signal, that is for sure. Along with that we will going to launch idler or pump, depending on which kind of wave we going to generate or we wish to generate. So, in some frequency generation it will be omega I, because omega s plus omega I is equal to omega p. This equation is a fundamental equation for this nomenclature or treatment that we always follows. And secondly, when we try to find out omega I, which is nothing but the difference between these two frequencies omega p and omega s. From this equation we can readily find omega I is equal to, from this omega I is equal to omega p minus omega s. So, that is we will going to launch these two, and the difference between these two basically gives omega I. So, this is nothing but the difference frequency generation, but the nomenclature is different. One should remember the nomenclature: omega p is pump, omega s is signal, omega I is idler. Omega p is normally greater than signal and idler. So, omega p is omega s plus omega I, that one should remember. And also in all cases one should consider that omega s is launched always. That means, signal is always in the left hand side. It will going to launch, we will going to launch signal every time. So, in some cases pump will going to generate, and in some cases the difference frequency will going to generate, or idler wave will going to generate. Okay. Next, once we have the nomenclature in our hand, we need to express the fields for three cases. So, these are the field expression for three cases. It is exactly the same thing that we have been using when we use the nomenclature as 1, 2 and 3. Here we will going to change slightly, that for omega pump we write omega p, and at the same point we will write amplitude as EP. EP is the amplitude of the pump wave, Kp is the corresponding wave vector, and omega p is the frequency. For signal it is same, omega Es is the amplitude of the signal, Ks is the wave vector, and omega s is the corresponding frequency. For idler also I can write Ei is the amplitude, Ki is the corresponding wave vector, and omega I is the corresponding frequency. All the cases the equation omega p is equal to omega s plus omega I is valid. So, this is our fundamental equation. In terms of k, it is Kp is equal to Ks plus Ki. So, momentum, and this is the energy conservation equation, and this is some sort of momentum conservation equation that is here. So, after having the nomenclature, now it is time to find out one important thing, and that is the corresponding nonlinear polarization term. When these three waves are there, so now these three waves already I mentioned, this is the three waves that we have in the system. Once we have three waves, the total field E is now represented by the pump field, the signal field, and the idler field. This is the total field. What should be the value of polarization, where the total field is represented by these three? Again I have written here in the right hand side. What about the polarization? We know that the polarization, non-linear polarization rather, is equal to 2 of epsilon 0 d in the scalar form, simply E square. So, this E is now E omega p, E omega s plus E omega I. So, once I put this E in terms of omega p, omega s, omega I, it should be E omega p plus E omega s plus E omega I and whole square of this quantity. When I make a square of that, now the interesting thing will come, because I am making the square of this plus this plus this. So, because of this square term, the frequency mixing will be there, but we need to find out what is the value of different, what is the value or what is the different frequency that I am looking for, that is important here. So, let me see it here. So, P N L of omega p, that means this is the P N L term. This P N L term contain many terms, because when I make E 1, so this is A plus B plus C whole square, something like that, but also the complex conjugate terms are there. So, I am making square of that. So, we will have A square, B square, C square plus 2AB, 2BC, 2CA, this kind of combined term will be there. Whenever I have AB, BC, CA, then we will have the addition of all these terms. So, omega p plus omega s plus omega I, or omega p plus omega I, these kind of terms will appear. Not only that, because of this complex conjugate, we will have omega p minus omega s or omega p minus omega I, this kind of terms is also there. So, I left this problem to the student to find out how many different frequency component you can have for this case when EP, E omega s and E omega I is shown here. But by just inspection you can find many things, that is the important thing. You need to look very carefully, and when you look very carefully by inspection you can find many things. Here for example, there are many terms in PNL, very frequency terms, but if I want to find out what should be the frequency term, what should be the PNL containing the frequency omega p, then we need to look this term very carefully. So, how the omega p can be generated? First term is omega p, but we have a square term, that means it should be omega p square, so we are not going to get omega p. So, omega p can only be generated with two terms, because in our hand we have omega p is equal to omega s plus omega I, this is always true. So, that means omega s and omega I, when these two terms will multiply each other, then I can have omega p frequency component term. So, in this a plus b plus c whole square, we will have one term 2 abc, 2 ab, 2 bc, 2 ca. So, here this term and this term, when these two terms multiplied, then we will have a frequency component omega s plus omega I. Omega s plus omega I is nothing but omega p. So, now if I take these two terms from here, omega s and omega I, and multiply these two, we will have omega s omega I, which is here. A 2 term will be there because it is 2 ab, 2 bc, 2 ca. So, this 2 will be there because of this degeneracy factor, and in the exponential term we have, since we are multiplying these two terms, we will have ks ki with a addition. So, we will have ks plus ki, and also we have omega s plus omega I with a negative sign, which is nothing but minus of omega p. So, that omega p is nothing but the omega p component that we are looking for. Also, the complex conjugate term, one complex conjugate term will be there, because all the complex conjugate term is sitting here. When you make a square of that, we will get all the complex conjugate. So, complex conjugate of this term one can also find. So, here one I is missing. So, you have to be careful enough. So, one I is missing here, I is missing here. So, this there will be I's actually. During the typing somehow it is not there. So, what about the omega s term? Omega s term is something which also we can find from this equation, whatever the mother equation or this main equation I am saying. So, omega s, here I can write omega s is equal to omega p minus omega I. So, omega p and omega I, these are the two components that will be important here to find out omega s. So, omega p, that means this term, and omega I with a negative sign means the complex conjugate of this term. So, when I make a complex conjugate term multiplied by this term, then I will readily get this omega s term. So, complex conjugate, if I multiply, I will have Kp here. So, I will have Kp minus Ki. So, that is why here we have Kp minus Ki, and also if I have Ep and complex conjugate, that means I have Ei star here. So, I have Ei star here, and the frequency component is simply omega s, because I am getting omega p minus omega I. So, minus omega I is coming from this complex conjugate term, and I am getting this. Also PNL omega I, PNL omega I, how do I get that? PNL omega I is again I can find out from this equation. So, omega I, mind it, here we should have one I sitting here, I, it is a typing mistake, that is why this I is missing. This one, from here we can see that when I multiply this and this I will remain. So, what about the last term? So, omega I will be simply omega p minus omega s. So, omega s is negative. So, that means I am using this complex conjugate multiplication of this complex conjugate with this term. So, when these two terms will multiply to each other in this a plus b plus c whole square term under this term, then we will have a Kp Ep, which is this Kp minus Ks as usual as the previous case, and this complex conjugate. So, we have E s star. So, E s star. So, once we have these three equation, then we have the equation of p nonlinear for omega p, omega s, omega I, and also the total fields. So, now it is time to derive, once we have these things, now it is time to derive the corresponding equation for that, the corresponding equation for that. So, equation means I try to find out the evolution. So, my goal here is to find out the evolution of this E p dz, how this term will be there, d E s dz, how this term will be there, and d E I dz. So, this term we will going to find out the evolution of pump signal and idler. So, now we will going to use our old Maxwell's equation with nonlinear polarization term. So, this is our Maxwell's equation in nonlinear polarization term. E is given. So, when I make a grad square term, because first term when I evaluate, I will get the second derivative of the first term, second derivative of this function which gives this thing, and 2 of the first derivative of first term and second term. This is the standard procedure that we have already used in our previous calculations. Then we will have these things with exponential term sitting here. Now, this in the derivative, this second order term is much smaller compared to the first order term. So, what we will do? We will going to neglect these things. So, we will going to neglect this thing. Once these things is neglected, the equation is relatively simpler, and we will get 2 I of K p del E p del z is equal to minus of K p square E 2, and then multiplication of this exponential term, and complex conjugate will always be there. So, one thing you should remember that here we are trying to find out the evolution of the pump. You can do the same thing for signal and idler. Only thing is that you need to just put proper PNL and proper electric field function, so that you can solve this equation in terms of their amplitudes. Well, once we have the value of these things, the value of the grad square, then we will have the second equation part, that means time derivative. So, time derivative, this is the total expression. So, I am making a time derivative. So, when I am making a time derivative with respect to that, then only this exponential term containing time. So, we will have minus of omega p. So, once we have minus of omega p, we will get this term here with a half, because half is already there. What about the polarization term? Again here I is missing, so you have to be careful enough that one I should be there. In all cases exponential I is somehow missing. So, when I making a derivative with respect to t for p nonlinear, the time is sitting here only. So, we will again have 2 term omega p twice I omega p and I omega p. So, there a negative sign will be there, and omega p square term will be there. 2 is already there. So, 2 and 2 will cancel out. So, we will have a term like this. So, now all 3 terms are in our hand, derivative terms, space derivative, time derivative for both the cases is there. So, I just put these 3 terms together in the nonlinear Maxwell's equation. Then the first contribution is this, the time contribution here I can write in this way, because omega p square is multiplied by mu 0 epsilon in the equation, and then omega p t is same for all the cases. So, I will just cancel it out. So, when I cancel it out, I will have only the term containing K p. So, in the right hand side we will have this term, and this term is multiplied by mu 0. So, mu 0 multiplied by epsilon 0 as usual, and d E s E I, which is the amplitude term here, and 2 omega p square with a negative sign is sitting here. So, now we will see that this term and this term will cancel out. Why this is cancel out? You can see from here. This is the equation, this is the expression which suggests that how these 2 term will going to cancel out. Now, after cancelling out these 2 term, we will have 2 I k p these things e to the power this and this. I can write this e to the power k term here. So, it will be e to the power minus of I k p minus k s k I, and in the left hand side we have this. So, just solving in 1 or 2 step, I can write this is my expression where delta k is this quantity, and finally, we will have the expression of the pump field and the evolution of the pump field, and the evolution of the pump field of the amplitude of the pump field rather is d E p d z is equal to I d omega p n p c E s E I e to the power the phase term. This is exactly the same term that we have derived in our second harmonic generation process. In second harmonic generation process, the process was degenerate, because from omega I can generate omega 1, from omega I can generate 2 omega, but here what we are doing, here we are generating this. So, please note this change. So, here my formula is omega p is equal to omega s plus omega I. Now, in this case, from omega p is generated from omega s and omega I. So, omega s and omega I are generating omega p. If omega s and omega I are not same to each other, then it is non-degenerate case. But if it is omega s is equal to omega I, then we can have omega p is nothing but 2 of omega s, which is nothing but the phase matching, the second harmonic for this, and the phase matching here is also like same. So, in that case, if you remember, delta k was k 2 minus 2 k 1. Now, k p if I consider 2, then k s and k I, if I say this is same, because omega s and omega I consider same. So, here also I can write k s and k I, they are same. So, k s and k I can be represented 2 of k s, which is nothing but here I. So, the fundamental wave or the signal. So, we are getting the similar kind of expression, but since we are dealing with 3 waves, so we will supposed to get 3 equations. So, one equation I am getting. So, now it is your job to find other 2 equation. If you find the other 2 equation, then the other 2 equation will come in the similar way, and you will get these 3 equation in your hand. This is the 3 evolution equation of the wave. Please note carefully that this is the equation we have derived here in this class. So, these 2 equation I asked the student to derive by himself or herself, and one can readily find out the relationship between these 2. So, for signal what is changing, here omega s will come, n s will come, and these 2 term you can see that omega p, if you remember, then you need to if you remember this simple thing, you do not need to remember all this calculation or all this equation. You can it can come very nicely to your mind, that if omega p omega equal to omega s plus omega I, so electric field containing the frequency omega s can be represented in terms of omega p and omega I is like this. So, omega p and omega I, omega is negative. So, the field here has to be p, and for negative omega I it should be E I star. These 2 combination can only give you omega s. In the similar way, you can understand for E I, that means idler is how much? Omega p minus omega s. So, that means we will have omega E p here, and for this minus omega s we have E s with a negative sign. For phase matching also we will have the same thing. Here we are dealing with omega s, omega p. Omega p is minus of k s, k p, k s, k I according to our notation. So, once we have minus of k s, k I, these things, when I have k s, so what essentially will do that k s will come forward, k I will come, and then k p will go. So, that means one negative sign, additional negative sign will be there, because here we can see that E p multiplied by E I star. So, E p contain k p and multiplied by k I star will be minus k I, but also I am having a term which is plus of k s. So, let me write it clearly. So, the first term here it is k p minus k s minus k I. So, here I need to find out what is my s. So, when the s is here, so there will be a negative sign, because k is these 2 things have to be positive, and then we will get the rest of the results. Well, I believe the students that they can derive these two equations the way it is shown here. So, they can derive that. So, now one thing we need to discuss here quickly, that is the collinear and non-collinear type of phase match. For collinear phase matching, we can see that they are in the same direction, this kind of phase matching. So, this is the phase matching condition. So, delta k equal to 0 is the phase matching condition, and in vector diagram we can say that it is happening when these two are same direction, but there is a possibility that they are not in same direction. If I consider this is a vector notation, so this vector and this vector, they can add to generate this vector, and they can follow a triangular rule to get this non-collinear kind of phase match. So, this is a different kind of phase match appear when we are dealing with 3 different waves. So, now how to find out the phase matching? What should be the angle, that is important. For non-collinear kind of phase matching, so this is our delta k. Delta k means this is the mismatch that we have. This mismatch will be minimized. One can see very easily this mismatch can be minimized when this is in same line. For example, if we have this, and if I this, and if this is my delta k, so this direction is not the preferred direction, because this delta k is not the minimized delta k. So, this delta k will be minimized when it is in the same line as shown here. So, how to find out this alpha and what should be the amplitude for which we will getting the phase matching is shown here. Once we know this is in the same line, so that means they are following a triangle, that is the condition. So, if this is psi and this is alpha, psi is the angle between the I and Kp, where Kp is the propagation constant of pump and I is the propagation constant of idler. So, now if I try to find out the different components, you can see that the components of Ki, Ks, and this is the components, the x components, and if I add this all the x components, I will get the total Kp, because Ki can be represented in terms of this and this. If this is Ki, if this is angle is psi, so this component is Ki cos of alpha. In the similar way, if I write Ks also I can divide into 2 parts, one is this and is a perpendicular component. So, this component which is here is simply Ks of cos of alpha, because this angle is alpha. In the similar way, for delta k also I can divide into 2 parts here and here. Since this is alpha, so we have this is alpha. So, once we add all these k component x components, so it will be this plus this plus this. So, these 3 things will give you the total Kp. Kp is the amplitude which is in this direction. So, from here we can write delta k is this quantity. In the similar way, I can divide this into perpendicular components. So, if I do, so perpendicular component this direction is perpendicular direction is this. So, if I divide, if you look carefully, it is in downstair, it is also in downstair, not in upstair. So, if I add these 3 things, so this has to be 0, because there is no perpendicular component of Kp, it will not going to equal to Kp any component of the Kp. So, that is why this is 0. Once this is 0, since this perpendicular component are vanishing each other, then I can have delta k sin alpha into this quantity. From here to here, if I divide, then this is coming as sin of alpha plus cos of alpha is coming as this. After having this equation, what we do? We just simplify this. This is the equation that we are having. So, we are simplify this, and when we simplify, multiply this and this, we will find that one term sin alpha cos alpha multiplied by k, sin alpha cos alpha multiplied by k with a negative sign, that will cancel out, and eventually we have tan alpha is this. So, that means I now have a direction along which the k should go. If this psi is given to me, if k I, k p and k's amplitude is given to me, there is a possibility. So, k I, k's this amplitude is given. So, I can find out what is the value of this alpha. Also the value of k p I can find, because we know that if in the triangle these two is given, the axis, these two sides are given, and if one angle is given, then this square, that means k p square, k is square, and the angle between these two, this has to be k s actually, this has to be k I. So, this thing can give me the value of delta k, because these things and k plus k s, k I plus delta s should be the value of the other sides. So, this square plus this square minus these things is a side which will be equal to this. So, when we calculate these things, we also find out what is the value. So, k p, k s and their angle is given and k I is also given, then I can optimize the value of delta k. Delta k is the phase matching. So, phase matching is 0, you can see very easily from this equation. If delta k is equal to 0 or if psi is equal to 0, then we will have the collinear form of equation. So, this is a general form, and this general form we can find out what is the value of delta k and the angle for non-collinear case. So, with this note, let me conclude here. So, today we have learned the 3-way mixing case in detail. So, in the next class we will go forward with other issues. So, with this we will like to conclude the class here. Thank you for your attention and see you in the next class.